Our fourth lesson on 7.3, simplifying radicals, we're going to go back to the quotient rule, and I'm going to show you a couple of things about how the quotient rule can be used two different ways to simplify radical expressions. Again, I have the list here of perfect squares, perfect cubes, and perfect fourths, so if you don't have those written down, you might want to write those down again, but if you have them written down already, no sense, you don't need to copy them if you don't want to. First problem and example here, I have the square root of 75 over the square root of 3. So I'm going to show you one way to use the quotient rule. One way with the quotient rule says that now I have a square root on the top, square root of the bottom. I can just keep the two separate. I know that in the square root of 75, I can change that to the square root of 25 times the square root of 3 over the square root of 3, which then becomes, top then becomes 5 times the square root of 3 over the square root of 3. Well, the last thing I do with this, I have a square root of 3 in the top, square root of 3 in the bottom. Since I have a common factor, top and bottom, a number divided by itself equals 1, then these will now cancel out, and I'm left with the answer of 5. So one way to use the quotient rule is just work each top and numerator and denominator separately like I did on this problem, and then you can get all the way out and then cancel out common factors if possible, and then you'll have your final answer. Another way to use the quotient rule, and I'll show you with the same problem again so you can see you can get the same answer. I have the square root of 75 over the square root of 3 again. I can then change this because the quotient rule says the square root of those separately is the same as the square root of the two written as a fraction, 75 over 3. So what I can do is simplify inside the square root symbol or the radical sign first, and then I can do the radical. Doesn't matter which way you do it, it will work. So now, what is 75 over 3 equals? 75 divided by 3, well, that's 25. So I can rewrite this then as that's the same as the square root of 25. And the square root of 25 is 5. Now, this is just one example, but it has been proven algebraically that it works. But you can do problems either way. You can do it as a numerator separate, denominator separate, cancel out in the end, or treat it as one square root over a fraction, because maybe you can simplify the numbers first, and it might get you to an easier number to work with under your radical sign. Either way works just fine. Some problems you're going to want to do it the way I did it in the blue problem. Sometimes you're going to want to do it the way I did it in the red. Okay, let's take a look at another problem. The square root of 80y over 3 times the square root of 5. A couple of things to look for. Since I'm doing a square root of 80, I want to look for factors of 80 that might be perfect squares. And then I also want to see, maybe I'm going to look for along the line, maybe I can get a square root of 5 on the top. And if I have a square root of 5 in the numerator and in the denominator, it's going to allow me to cancel a radical out. That's also making it simpler. So looking at the factors of 80, if I'm going to see if a factor of 5 works, let's see, what's 80 divided by 5? 80 divided by 5. Handy dandy calculator. 80 divided by, wrong button, divided by 5 equals 16. Hey, that's a good thing because I know 16 is a perfect square. I'm going to change the top of this fraction. I can't change it into a fraction like I did in the red one. I'm going to have to keep it separate. But this is then the square root of 16 times the square root of 5. And I like to write the perfect square first because I know I'm going to simplify that later. And then this is times the square root of y. So I've now separated the variable factor from the numerical factor so I can work with them. Then the bottom, 3 times the square root of 5. There isn't anything I can do with that, so I'll leave that as 3 times the square root of 5. So now I have everything on the top is multiplying, and on the bottom, I'm also multiplying 3 times the square root of 5, which means now I can look for common factors between the numerator and denominator. I have a common factor right here, square root of 5 over square root of 5, which means that is 1, so I can cancel that out. Then I have the square root of 16, so that's 4, times the square root of y. Can't do anything with square root of y, because y, the term y itself, the exponent is 1, so that's not a perfect square. And in my denominator, I have 3. Now, this is a correct answer, 4 times the square root of y over 3. You can also rewrite this as this, 4 thirds. And some people like to write it this way. Some textbooks answer keys will have it written this way. Some will have it written the way I had it originally. Some answer keys will be like this, and some will be like the second one here. The reason they do it with the second one is I separate the rational number. 4/3 is a rational number. The square root of y, as far as I know, is irrational, and it's unknown. So I can leave it either way, but you might see it one of these two ways in an answer key that you look up in your book or in mine. Okay, another example for us. Here's one where now I have cubes. 5 times the cubed root of 162 x to the 8th and the cubed root of 3x squared. This is one you can do it either way. When I see problems like this, first of all, I'm going to look at the numbers here. And I look at it and say, can I take 162 and divide it by 3? Well, the divisibility test for 3 is if you add up the digits, 1 plus 6 plus 2. 1 plus 6 plus 2 is 9. Is 9 divisible by 3? Yes, it is. That means since the sum of the digits is divisible by divisible by 3, the number itself is divisible by 3. So I am going to do this. I'm going to write 5. Whoops, I'm going to change this. I would like this to be a little bigger. I'm going to have a good old-fashioned 5 written out here. Great big one. Because this is like 5 over 1. So I have 5 times, and I'm going to say the cubed root of, and I'm going to make a big cubed root symbol, and I am going to use the product rule, that part of the rule that says I can put both of them under the same radical sign, and I'm going to divide the fraction before I deal with the radical. Sometimes by dealing with dividing the fraction again, it simplifies the number inside, and we can work with it easier. So what does this all equal? I'm going to keep the 5 on the outside. Okay, I know I'm going to have a cubed root. What's going to be inside that cubed root? 162 divided by 3. 162 divided by 3. If you don't know it off the top of your head, bring your handy dandy calculator up. 162 divided by 3. 54. So I have a 54. The question is, will I have a fraction? I don't think I will. So I have 54. So I've taken care of the number part separately. Here, that's what I worked with. Now, x to the 8th over x squared. I will subtract these exponents. X to the 6th. X to the 6th. The question is, am I done? Is 54 a perfect cube? No, but I must ask myself, what are the factors of 54? Are any of them a perfect cube? Well, let's see, factors of 54. 1 and 54. 2 and 27. There's a perfect cube right there. Okay, now I know that I'm not going to go any further because if I keep going down with factors, there are more factors, such as 6 times 9. But 27 would be the largest perfect cube I could find here. So I'm going to stop here, and I'm going to rewrite this as 5. Oh my goodness, that was a mess. 5 times the cubed root of 27 times the cube root of 2 times the cube root of x to the 6th. So that leaves us with 5. What is the cube root of 27? Let's look up above at our perfect cube list. 1, 2, 3. Cube root of 27 is 3. So 5 times 3. And then I have times the cube root of 2 times, and what's the cube root of x to the 6th? Oh, it's an even number. Can I divide? Remember, the shortcut is I can take the exponent here and divide it by the root number I'm after. Yeah, 6 divided by 3 is 2. So that is x squared. So then I have 5 times 3 times the cube root of 2 times x squared. And I'm going to change that. The order of this, 5 times 3 is 15. And I will say 15 x squared times the cube root of 2. And at that point, I am done. I have now factored out anything that's possible to give it meets rational numbers here. What's left over here is times something that is irrational. And at that point, I will stop. Okay, your answer, your assignment has already appeared on the screen for you. It's page 435 and numbers 59 to 71. And please turn it in after you finish, and please check your answers. It's very important that with all this exponent work and all the numbers you're working with, check your answers so I can help you if you need help, or a friend can help you, because I don't want you going beyond this without understanding what you're doing. Okay, copy down your assignment. Let me know how I can help you.